Okay, now I can get started. We're recording. Darren, I'm going to turn you loose here in a moment. But this is the 100 book.
What page is that?
This is page 2-2. But it says electronic and conventional current. I'm actually just going to read it. Electrons move in the direction of positive voltage. This is called electronic current. Conventional current takes the other point of view of positive charges moving in the direction of negative voltage. Conventional current was the original model for electricity and results from an arbitrary decision made by Benjamin Franklin in the 18th century when the nature of electricity in atoms was still unknown. I wish I had a time machine so I could go back and correct him. Anyway, it can be imagined as electrons flowing backwards and is completely equivalent to electronic current. Conventional current is used in nearly all electronic literature and is the standard used in this book. The direction of conventional current establishes the polarity for most electronic calculations and circuitry diagrams. The arrows in the drawing symbols for transistors point in the direction of conventional current, for example. Straight out of the book. I have a hard time understanding it. But now I'm going to, by the way, this is a transistor, and when Darren's done talking, I will explain that. There's the arrow. Well, I was going to have you have them build this circuit.
Okay, let me power mine down here.
And just as a reminder, if anyone is still pinning Joe, you need to remove his pin by clicking on remove pin.
Oh, yeah. You should be pinned on Darren.
Well, I can pin on Darren, but I was pinned on you from before, and I think everybody else that we instructed to pin on you was also pinned on you. So I'm going to tell them not to pin on you anymore because they won't see Darren if they pin on you.
What does this circuit do?
It teaches you how these things work.
Well, can you be more specific?
It's a very low level heater. That's honestly all we're doing is burning some current here in these resistors and very gently heating them up.
Okay.
So this is what you had before, right? Does everybody have theirs still built with the LED on it?
No.
Okay, you need to. Joe, do you want the LED in there, or you want to just focus on the resistors?
Oh, we can have the LED.
Okay. So here's the schematic we're looking at. Same thing we had before, the battery, input capacitor, the regulator, output capacitor, LED, and the resistor. And then we've got the three 100 ohm resistors that Joe drew in series here at the end of the circuit. So here's the drawing for how to do that. Here's the first part, the regulator, the two capacitors, the resistor, and the LED. So if you don't have that built, you're probably going to want to try to get that put back together if you can, just as it's illustrated up here. And I would say what you should do is get that built first. And my little negative lead off the battery clip is not helping here.
Should they have been soldered, Darren?
Oh, we should have probably, or stripped a little more off. Anyway, we need everybody to let their little light shine. let's get to that point first, and then we will build on from there. So you should be able to put that together with your LED and your voltage dropping resistor. And when you get your light shining, we're ready to go to the next step.
Can you explain briefly what the regulator does, why we have a regulator?
That's a good question for Joe. All it's doing is dropping an unknown voltage between 6 and 30 volts down to 5 volts so that we can work with a 5-volt circuit.
That's my answer.
Yep, it takes, if we had a 12-volt circuit from our car and we needed 5 volts for what we're doing, this is how we would get there. It's just a built-in regulator that drops the voltage down to 5 volts and limits the current.
Okay, thanks.
Does it do that by a resistive means? And if so, how does it dissipate the heat?
That's such an easy question. I'm going to let Joe answer that. No, actually, it is a combination. And let me go back here to a drawing that was kind of in a pile across the room. That is the circuit right there of what's inside that little voltage regulator. So you can see it's fairly busy. Some transistors in there, some other components to make that work. And it dissipates the heat through the body of the component. And I was actually checking as we were doing this earlier just to make sure that I wasn't overheating it. It's actually sitting pretty warm running my little LED.
So it's ultimately it's resistive, I guess.
Yes. That's how it dissipates the voltage.
Okay.
Yeah, Darren, if I may,
Yes, sir.
this is one of the lessons that I want to teach all of you is the ratings of equipment. And this device is rated for 100 milliamps. That means if you exceed 100 milliamps, you can or you may or most likely damage the device. And what it works by dissipating the excess between the 9 volts and the 5 volts. So if you use Ohm's law, you take 5 volts, and we're gonna talk about watts. And you take 5 volts times the current, which is 20 milliamps. I'm sorry. You subtract 5 volts from 9 volts, which leaves 4 volts. And it's 4 volts at 20 milliamps. So 20 milliamps times 5, and I don't know what that is.
100
100 what? Milliwatts?
millivolts if you were doing voltage.
No, voltage times current.
Oh, so
Is
it'd be watts. Yes.
100 milliwatts.
Yep.
100 milliwatts, which is 0.1 watt. And that is dissipated as heat in the device. Now, the next one that we have, this is a 78LO5. The next one we have is a 7805. And that's rated typically at 1 amp. So you could draw an amp out of it. So if you've got 9 volts and you're drawing an amp, that would be 4 volts drop times 1 amp, which is 4 watts.
So
That's
if you're
a lot.
putting 12 volts into it, you would need to have a higher wattage rating.
Yeah. Yes, you're going to dissipate more heat, lose more power.
Yeah. Yeah, but in your package is a switching supply. And it's about the size of that device. Darren, do you happen to have it there?
Yep. Just a second, I'll get it.
Yeah, it is a switching supply. That little guy right there, you can draw 3 amps out of that, and it won't hardly generate any heat at all. But it does it by switching, and later we will get into that and why that's more efficient. And that's why so many things use switching power supplies. But that's way down the road, guys.
All right, so does everybody have their light working? Circuit board together, light working? Okay, so next step, we're going to remodel a little bit to match this here because we need some more room to build. So we can take that negative wire off and we're going to put it down here on column 2, down at the bottom. Mine is a little uncooperative. Mine is becoming more uncooperative. Okay, so just like we have here on the drawing or on the illustration. And then what we're going to do is we're going to lengthen that negative bus because we need to hook up more things to ground, to negative. So we're going to do that with the jumper. Okay, so now our circuit is back together, our light is on. So we've moved the negative of the battery down here to the bottom. And then we've added this jumper up to the negative at the top. So column 2 is all negative. That's that bottom rail that we see in the schematic. Okay? And I will tell you, when I do these, if I'm trying to build something or put it together, I can't keep track of it, so this is how I do it. As I build something on there, I highlight it on the schematic so I know, all right, I've built that part. I know I've built this. We know we've connected our regulator. We know that we have the output. We know we have our light on with the LED. So I've built all these things already, right? So now we're going to build these 3 resistors at the end. Those are the next things in our circuit.
And those resistors are in
Series.
series.
Those are in series. So just like we have illustrated here in column 2 over to column 5, we're going to put one of these resistors. So I've got my first one in there. Joe, do you want to do these one at a time and measure, or just put them all in there? Probably build it, huh? And then we'll just measure in between.
Yeah, let's build it. Yes.
Okay. All right, so that's our first resistor.
Darren, you asked me to make an executive decision.
Sorry. I thought you were an executive.
I'm getting tired. That's why I have you do the second half of this.
All right, so there's our second resistor, which is from column 5 over to column 8. So this guy right here in the middle. And I apologize, I'm not using Joe's special blue resistors, but these will work. And then we're going to extend that one more time with another resistor. The third one in our series from column 8 to column 11, or wherever you end up there. I kind of did mine shorter, sorry. Or I don't have enough lines on there, I don't know. I guess the block is bigger than that. Anyway, that's what we're after. 3 resistors in series. So now I've built this and this. How we doing?
Doing well. Now what I would do is measure the resistance starting at the left-hand side and then using your ohm meter to look at it.
Okay, so if we're going to measure resistance, we're going to do that without the power on the circuit. So we'll take that little negative wire off, get it out of the way. And we will put the meter on something that looks like resistance. Got the little ohm symbol there, so that should be good. And we're going to, I cheated a little bit and got these other little fancier leads because it's easier. But we're going to look at all three resistors in series.
Actually, I wanted to, well, that's fine. I
Oh,
wanted
you want to look at each one.
one, 2, and 3.
Okay, sorry. One resistor, the first one, pretty close to 100 ohms. I'm showing 99.7 on my meter, but that's
Are those 1% resistors?
no, they're not precision.
Oh, okay.
I don't think it's a 1% meter either.
Oh, that's
But-
our Astro AI.
Okay, so there's 100 ohms. We'll go over here to the second. So now we're using two resistors. And we're pretty close to 200 ohms. So let's go through all three resistors. And we should be at about 300 ohms, which we're pretty close. All right, does everybody have that put together? If you don't have a meter, that's, I suppose we'll still be okay, but it should look about like that with three resistors in series. All right, now what, Joe?
Okay. Now what, let's apply the power. Except that,
We don't have the switch in there yet.
no, we do not.
All right, so all I'm powering right now is my LED.
Correct.
These three resistors just go out here to this last column and don't go anywhere else. And we
Yeah.
know that electricity doesn't work if we don't complete the circuit. So we're going to do that with another jumper.
Yeah, Darren,
Yes, sir.
I'm gonna have you go to the second resistor instead of the third.
Okay. So that would be right here. Joe wants us to connect to this, which is column 8 here. And we'll put a jumper in that column. And then to complete the circuit, we have to take the other end of that jumper and go to our 5 volts, right? Which is the output of this regulator, which will be on column 3 on the top, like that.
Now, measure the voltage of the two resistors.
You didn't say please.
Please, sorry.
Okay.
Just keep me in line.
You want the voltage across those two?
Yes, both of them.
Okay. So we're going to go through those two resistors and measure the voltage.
14.966 volts,
Almost 5 volts.
which is within the range of what our regulator should do. Now I'm going to have you, and if you'll take your pencil and point to on your schematic between those two resistors. No,
That's where we're measuring right now.
no, your wire's hooked up to that point. Oh, yes, that is where you're measuring right now. But what I'm
Yes.
going to do is have you measure in between the two. But before we do, I'd like some people to tell us what the voltage should be. Did you follow what I said?
You want me just across the first one?
Not yet.
Oh, sorry.
Ah, dang it.
What Joe is alluding to we'll put this at ground and this at plus 5 volts, right? Two resistors. And Joe wants to know what this voltage is right here. Because he wants you to understand this is a voltage divider circuit.
Exactly.
Does that make sense? We put some in here if you're going conventional. And if these two resistors are equal, What do we think that voltage would be in the middle?
2.5.
That's a pretty good guess.
Correct.
So we've just divided that voltage in half with two equal resistors.
That's called a voltage divider. Now let's do it with all three resistors in there.
Okay, so we're going to move the jumper over here. If I get it in the right spot.
Okay, now show them on the schematic where you're hooked.
Okay, so now, oh, I don't have to get rid of this. So now we're measuring here and here across all three resistors in series. And we have 5 volts.
Right. Now let's go back to that same junction you went to before.
The first one,
Yeah.
you got to guess first or calculate?
Oh, anybody want to guess?
1/3 of 5 volts.
3 1/3.
No.
I like the 1/3 of 5 volts. I don't know what that is. Anybody got a calculator?
It's about 1.7, I think. That's my guess.
I think that's awful close. Now go to the next one, number 2.
Two-thirds of 5 volts.
Correct. 2/3 of 5 volts. That's a voltage divider.
So these are the places we were looking on the schematic here. So we had 200 ohms on one side and 100 on the other side, so it's not going to be equal. And then we had 200 on the other side and 100 on the original side. So divided into thirds. Now what, Joe?
Okay, well, we've got the parallel situation.
Okay.
there.
All right. Well,
But before we go on, does anybody have any questions? Nothing?
So if you were to measure the current, let's say you placed a load on one of those taps in the series of resistors, would the current be unequal on both sides of the circuit? I mean, I guess you'd have to ultimately connect it to the negative side or the other end of the circuit, I guess, is what I'm trying to get at. Would you end up with uneven current levels on both sides?
No. The current stays the same through the whole circuit. So Darren, just point to the bottom of the 3 resistors. Okay, so there's 300 ohms. That's 0.15 amps going through that, right? So there's 0.15 amps there. Now go to the next node. 0.15 amps there. Next node. 0.15 amps there. Next node. 0.15 amps there. It's always the same.
Okay. I think
Well,
what
it's
Robert's
measuring
saying
it.
is if you were to pull current from the junction of those 2 nodes.
Oh, that would change everything.
Yes.
Oh, sorry. Oh, sorry.
I think, Robert, is that what you were after?
Yes, exactly. Thank you.
Yeah, that makes a completely different circuit if we were to actually load those down. And that's something Joe and I were talking about. These are great for reference voltages. If you need to have 8.6 volts as a reference to do something, this is a great way to get it. But once you start drawing current through there to do things, it gets a little more squirrely and a little more complicated how you put that together.
So that would change the voltage division if you were to load whatever point you were testing it at.
I don't think the voltage would change. The current would certainly change.
Well, the current would change, so that would change the voltage.
Yeah, I guess it would. Yeah, I see what you're saying.
Because of loading the source?
Just because you're creating load here, yes, you're creating another resistance off the side of this.
Yeah, it used to be before the digital meters and that sort of thing. We used VOMs, where voltage, ohm, milliamp, ammeters, and it was just a meter movement. And when you stuck it in the circuit, it would load the circuit. So it would change the values. So if you were looking at a really high resistance area and you stuck your ohm meter in there, it would change everything. And with these digital meters, they're typically 10 million ohms impedance, which means, oh, an old Simpson. Oh, that's beautiful.
Yeah, so this was
Yeah,
the old,
they used
this
to
was,
be rated in like so many thousand ohms per volt, right?
Correct.
yeah, that's the old school way of doing it.
But with the digital multimeters today, that it's typically 10 million ohms. And so it has very little effect on the circuit normally. Although you can get into some real high resistance areas where it might have a little bit of an effect, but typically not. So
Okay,
anyway,
so we can break this down and move to parallel.
yes,
Okay, so what we want to do first, let's power this down. Because that's usually when bad things happen, is when you're swinging wires and components around with voltage on there. And you are going to want to take those resistors out. Maybe. And let me change to the next drawing and we'll build it differently. Ta-da!
oh Darren, you're so well prepared.
Not really, but thanks, Joe. Okay, so here we have 3 resistors in parallel. So we still have our jumper extending the negative bus down here, so we have lots of room to put these on the negative side. And then we're going to just put these 3 resistors parallel to each other. And then we're going to add our switch wire to heat that all up once we get it built. So 3 resistors, yes.
I'm going to ask you, I'm throwing a curve at you. Just put in one resistor. Do you have 2 meters? Can you actually measure the current?
Sure.
That's what I'd like you to see.
Okay.
I'm cold. I tell you, down here at this end by this window, it's cold out there.
Oh, it's cold here too.
We've got
Alright, so-
heaters running in here. It's not doing much good.
So I just have the one resistor, and I'm going to put my little jumper in here from column 3 down here to the resistor. Does that make sense, what we're doing?
Oh yeah.
We're just building this part right here. We already have that and everything else. We're just going to put this first resistor in the circuit. And where do you want me to measure current, Joe?
Yeah, it doesn't matter. The 9-volt battery is fine.
Okay. So I'm going to cheat here
Well, there you go.
and drop my meter in between the battery and the circuit. And see if we can make something burn or smoke. No, not yet. Good.
Oops.
So with our LED in there, oh, you don't want that there, do you?
No. Take it off.
Oh yeah, can't do that. Sorry.
Yeah,
That warmed up that regulator quite well.
I bet it did.
Yeah, I touched it. It's like, oh, no, don't do that. All right, so now we're measuring how much current the whole circuit is drawing.
Now, actually, can you pull out the LED momentarily?
Sure.
So, that's 52 milliamp. What was it with the LED in?
70 something, maybe?
Uh,
Almost 80?
boy, that's 30 milliamp. I'm surprised. Okay. Now, can you, oh, this is, do you have another meter where you can measure the voltage right now?
Sure. Where do you want me to measure voltage?
From the ground to the positive.
Well, whether we can get on that easy, I don't know.
Well, what about
Okay.
on the,
All right, yeah. To the output of the regulator?
sure, or the other side of the resistor,
Okay.
4.91.
Almost 5 volts. This is a cheap meter.
Yeah, well, that's okay. All right, well, put resistor 2 in there. Does anybody know how many ohms there will be now? With 2 resistors in parallel? I don't hear any answers.
50?
50.
All right, good.
Keep your finger off the regulator, by the way.
Is it getting
It's-
hot?
Yeah, it's warming up.
Now, this is a 100 amp regulator, and it's putting out 130
100
milliamp.
100 milliamp regulator?
Yes.
All
What did
right.
I say, 100 amp?
Yeah.
Oh, no, that's
Be
100
much
milliamp.
shorter exercise.
Yeah. Yeah, now measure the voltage.
Okay.
Well, where's the meter?
Oh, you want to see the meter too. Geez, Joe.
Yeah, I know, I'm fanatic.
Well, if I could keep it on there. Oddly enough, it's still right around 5 volts.
Yep, yep. Well, let's not take too long. Let's put the third one in there.
All right.
Now, I've done this and it hasn't smoked it yet, but
Well, it's definitely a thermal issue on the thing, so
okay, now, okay, 180 milliamps.
yeah, it's warming up.
Okay, quickly measure the voltage.
Oh, sorry.
Oh, it's only
Still
dropped,
still at 5 volts.
it's only dropped 1/10 of a volt. Oh, with mine, it dropped to a full 1/10 of a volt. Okay, go ahead and turn it off so we don't burn it up. Phew. Well, that device, actually, yours held up well. Mine after it was on a few seconds started dropping in voltage.
Interesting.
Yeah, well, I think they have you know, if you have a short circuit or something, it'll just fold back.
Well, it's a nice design if that's what it'll do.
So anyway, well, folks, we have
13
exceeded
minutes.
the capability of our little 78 L05. Now, Darren, just grab your 7805 and stuff in there.
All right. This component may be warm, so if you're taking that out and putting the other one in, just understand that might be warm.
Yeah, disconnect your power.
Yeah, my power is negative leads off.
Oh, okay, good.
So here's the larger 3-tab regulator. And in this one, the pinout is different. So you want the writing on it. Maybe you can see that. I don't know. Hang on, let me get it up here.
I can't. Oh, there you go.
So there's writing on it. You want that to face towards you or up as we put it in that circuit. I got to refocus here. So we're going to drop that in the same spot that the other one was, but the writing is going to face up towards us.
Yours went in fairly easily. I had a hard time getting mine in.
I'm a trained professional, Joe.
Yeah, that's why I hired you.
I tried it several times before because I was afraid it wouldn't fit.
Oh, you got stuff broken in.
All right, so whoa, let's try to keep it up here. Let me find the other meter lead.
Yeah, something's happened with your light level, Darren.
Oh, sorry. Yeah, hang on.
There you go. There you go.
Thank you. All right, I will put some power back to it. And we're up and running with 180 milliamps.
Now that bigger device can handle up to an amp.
It'd pick up a little bit of voltage, but sorry, I keep forgetting that's out of your view. Hang on.
Do they require a heat sink to operate at their rated current level?
Which one?
Well, either one of them, actually.
The first one, no. It does not require a heatsink. The second one, yes. You can see the metal tab on there. It needs to have a heatsink on it if you're going to run a full amp through it.
And is the tab the output? Do you remember? Or is the tab ground?
No, I think it's ground.
I believe it is. So on a variable regulator, the tab is the opposite, I think. But, all right, so we had 4.94 volts and 182 milliamps. And actually, you can feel a little heat being dissipated in that. You squeeze that, you should feel a little warmth. It's just the electronic circuit telling you how much it loves you.
Yeah.
You don't want to exceed that warmth. You want to keep that to a nice, comfortable level.
So if the tab is not grounded, if it's the opposite, as you say, if you connect to a heatsink, does it have to be isolated from ground of the chassis?
Yes, absolutely. That's why I was saying that has stung me before, because it's a 317, I think, that's an adjustable voltage regulator in that same format, a 3-tab regulator like that, and you just put a resistor in there to determine what output voltage you want. The tab on that is positive, I believe.
Yeah.
So you don't want to mount that to your ground bus. You don't want to have a heat sink on there that touches the case or anything else. You want to be aware of that.
Or you can put an insulator in there.
Yeah. Lose a little bit of efficiency, but
yeah. Well, Darren, I think you've done wonderfully here. Does anybody have any questions up to this point? Did anybody learn anything?
Yeah. I have a question.
Yes. Go ahead, Rose.
Darren, can you show the end of your lead, your meter lead? Because it looks like it's so stable.
okay, so these are a little different.
That is so cool.
You see the little hook there, and it's spring loaded.
What's it called?
Well, I used to know the name, but I've forgotten, and I'm sure Joe knows it.
Spring loaded hook clip.
Okay.
Spring loaded hook thingy.
I like
so
the
yeah,
part.
you can get clip leads like this that have those spring loaded clip thingies on each end.
Okay.
Or what I bought was sorry, I'm digging in the other tools here. Was a set of these leads that plug into the meter on one end.
Mm-hmm.
So they have that kind of banana plug for your meter.
Oh, yeah.
And the other end is the super spring-loaded clip thingy.
That's so
And
cool.
it was like $4 or $5 on Amazon for 6 of them.
Okay,
you-
thank you.
You guys talk like all leads fit all meters. Is that a fair statement or not?
Fairly.
No,
I didn't think so. So Joe's
That-
intro about his leads was great, but they might not fit my meters.
that's the
Okay.
idea. But that banana plug is supposed to be somewhat universal. But whether it is or not, I don't know. But they fit the red meter, so
Okay, that's what I have, so I was just curious.
yeah, it makes it so much easier for this kind of thing where I'm going to be clipped onto it for a little bit to show something. It's hard to keep the connection on there and measure for very long.
Yeah, thank you.
Darren, I have a question. Is it possible for us to get copies of the schematics that we worked with?
Oh, I am so sorry. Yes, I intended. Wait, I sent those to Joe. I'm going to blame that on Joe.
Oh,
Joe
I just
would
mean
be.
if we could get them this week, then we could kind of
Yes.
review.
No,
what we
my
did.
apologies. I sent them to Joe yesterday for approval. And the idea was I was going to remind him to forward them out so you would have them tonight. And I failed to do that. So I'm sorry.
Darren, quit taking the blame.
Joe will send them out later tonight or tomorrow after he wakes up and has breakfast.
Great, thank you.
Oh, dear. I'm sorry, folks. Yeah. Yeah, I should have sent that out. We're we're learning how to do this. And so we're getting it down. We've got the audio in here working now. We've got I think that my recording will be much better this time to put on YouTube. And so we're making good progress. But Darren, can you allow me to take it over now?
Absolutely, unless you want anything else here.
No, I think that's it. We're down to about 4 minutes for the class.
Do we need any of this?
I asked everybody else, do we need that?
I think it's doing all right. I'm not going to tap it too much. Oh, meter's going to power off though.
Okay. All right, very good. Here is a schematic. Now please do not hold me on these resistor values. I just made this up as I went along for reference. But here is our battery. And we'll say here it is, it's 5 volts. We got 1,000 ohm resistor here and 1,000 ohm resistor here. So if this is 5 volts up here, what's going to be the voltage at this point?
2.5.
2.5, 2.5 volts. Now, this is a voltage divider, and that is how you provide the bias to this transistor. This is a transistor right here. This is the emitter, the base, and the collector. And see the arrow here? That is conventional flow. So you got the positive holes flowing this way, flowing here, flowing down here, and flowing this direction, like that. And this is an NPN transistor. But we provide this voltage here. If this is 2.5 volts, every time you have one of these junctions, it's about 0.6 of a volt. 0.6 volts. Now, one of the first things I learned at Tektronix when I was working there, that means at this point right here is 2.5 volts minus 0.6 volts, which then leaves us with 1.9 volts. So that's just part of troubleshooting and figuring out stuff and what things ought to be. So if you see a circuit like this and you know that you got a voltage divider and this should be 2.5 volts and you measure 2.5 volts there, And then you go to this point, it should read 1.9 volts about. And, you know, there are different kinds of transistors with different voltage drops, but most of them are about 0.6 of a volt. Anyway, that
Joe, how do we know that's an NPN by looking at it?
you had to ask that question.
Okay, we know that.
Okay, hang on. This, I usually do it this way. I think of it this way. This point right here is negative. This right here, this is negative, and this is positive. And so the positive draw goes through the arrow this direction. Excuse me, like this. So positive to negative. So that's NP, and then you call it N. That's how I think about it.
Okay, my cheat sheet for that is the arrow inside is not pointing in.
Okay. That
So-
works.
So I can look at that and I can tell that is an NPN transistor because the arrow is not pointing in. If it were a PNP, it would be pointing in. The arrow would be turned around inside the circuit, pointing inside. It's
Yeah.
just a cheat sheet thing that I can
Okay.
remember. I don't remember where, but just a glance at it shows you which kind that is.
So that's confusing to me because NPN not pointing in, that one apparently is pointing in toward the base of
No,
the trans.
the arrow is pointing outside of the circuit, outside of the component.
All right, maybe I didn't see it properly.
Joe, redraw that a little bit, or maybe
Well,
that arrow
here's a
right where
base. Here's a collector. And
you're
here's
off the screen a little bit.
Oh, oops.
Yeah, it's got so much writing on it now, I can't really see it.
Base, collector, and this is the emitter. And if the arrow is going this direction, and this is negative and positive, NP. This is a plus voltage and this is a negative voltage. Does that make sense?
Yeah, so that arrow is not pointing in. Can you draw a PNP real quick?
Yes.
Can you draw a horse? Just checking.
Here's the base, here's the collector, and here is the emitter. This
Okay.
is P, N, P. And I
So
look at this as positive to negative.
Yep, that's a good way to do it. I like that.
Now, wait a minute, back up a little bit. Not pointing in, NPN. Is that the analogy that I
Yeah,
understood?
we're just looking at the arrow, just looking at the schematic, and the arrow is not pointing in on the left, and on the right, it's pointing in, PN. Maybe I shouldn't have said that. Sorry. Just something I learned to look at them real quick. And NPN, the arrow points out of the component.
The arrow points out of the component, not pointing in, points outward. Okay.
I think it's a great analogy.
I was just saying it works for me. If it doesn't work for you, don't use it. Find another one that makes sense to you.
Yeah, in this transistor here, if this transistor has a gain of say 50, the current here, let's say it's 1 milliamp, the current through here will be 50 milliamps. And I just got the signal that
That's right.
we're out of time. Anybody have any last minute questions? see here. No questions? Well, we either taught you everything you ever wanted to know about electricity,
Or you snowed.
or we just snowed you completely under.
Well, you're ringing the
ladder.
bell, see?
Ladder,
You're
thank you.
ringing the bell, so we can't just keep going on and on and on.
No, well, I'd like to say good night to everybody and thank you for coming tonight, even though we had to do it this way. I'm gonna probably have to drive John home because I've got a rig that can handle the snow and the ice and stuff. So anyway, God bless you all and thank you for coming and have a good night. And I will do my best to get this online and then try to when I put it online, I will try to put links to these other things that you guys wanted. Anyway. Good
Okay,
night,
so you,
God bless you all.
thanks, Joe.
Thanks, Joe.